Hello. Today I'm going to discuss about adding touch buttons interface to your projects using the IC TTP228. So let us get familiar with this IC. This IC supports 8 or 16 touchpads, so you can make devices that has up to 16 touch input buttons. Later in this video, I will tell you how to select between the 8-key mode and the 16-key mode. I will also discuss in details the difference between these two modes. This IC needs a power supply whose voltage is range of 2.5 to 5 volts. Thus, it can be interfaced with both with new 32-bit MCUs, which runs at 3.3 volts, and also with older MCUs like AVR and PICs, which runs at 5 volts. This chip can give direct output according to the button's touch. This direct output could be used to directly drive loads. In this design method, we don't need to use any microcontrollers. Loads can be directly connected to output pins of this IC, but this method is only available in 8-key mode. The second interface method is serial data output, which is a very serial interface with a data out pin and clock input pin, but please don't confuse it with I2C interface. It is not I2C interface, but much simpler than I2C. Now let us see the configuration settings of this IC. This IC is highly configurable, and I am going to discuss them one by one. Single key multi-key type, 8-key or 16-key type, sensitivity adjustments of touch key, output type settings, i.e. active high or active low, output type function, i.e. CMOS type, open drain type OD, or open collector type OC, sleep mode sensitivity adjustment, maximum key on time, infinite or 80 seconds, sleep mode sampling length, 4 milliseconds or 2 milliseconds, sleep mode sampling rate, 8 Hz or 64 Hz. Let us see how we can configure this IC to suit our needs. In many ICs, configuration is done using integral registers. You write the configuration registers through some mode of data communication like SPI, I2C, or parallel interface. But in this IC, there are no registered interface, but a simple pin type interface. That is, you simply pull down some pin of this IC to choose a specific mode, and you leave this pin to select another mode. Let us understand this is an example, but we choose between 8-key or 16-key mode, as I have already told that this IC supports both 8 keys input and 6 keys input. So the question arises how we can choose between these two modes. For that, let us open the datasheet and see. Here they say these modes are selected via high-value register connected to the TP2 K-cell pin to VSS or not. That means if we connect a high-value register between the pin KYSEL and ground, we will have the 16-key mode. And on the other hand, if we do not connect any resistor to this pin, we have the 8-key mode. Simple. In this way, we can choose other configurations also. The value of this register should be 820 kiloohms. This is clearly mentioned in the datasheet. From datasheet, we found that the KYSEL pin is pin number 2, so we can connect register like this to get 16-key mode. In the same way, we can do other settings. So now let us see how we will configure this IC for our current project. The first settings we must choose is the single or multi-key function. We use single key function in this project, which is also the default setting, so we do not need to connect any resistors. Moving to the next setting, which is the sensitivity of touch buttons. Now this is the most important setting for TouchSense IC, since the overall sensitivity of touch buttons depends on PCB design, size of touch sensor pad, material of the enclosure, and its thickness. We need a way to adjust the sensitivity of touch after the product is fully developed in order to get optimal performance. For this purpose, IC TTP229 provides us a way to adjust touch sensitivity of touch buttons. Sensitivity adjustment is provided through 4 dedicated pins on this IC. They are named SEN-ADJ0, SEN-ADJ1, SEN-ADJ2, SEN-ADJ3. There are 4 sensitivity adjust pins, and each of them controls the sensitivity of 4 touch pins. For example, SEN-ADJ0 controls sensitivity of input pins TP0, TP1, TP2, and TP3. Sensitivity is adjusted by adding a capacitor whose value range from 1 pF to 50 pF from SEN-ADJ pin to ground. The IC has separate settings for sleep mode, that is low power mode. Sleep mode sensitivity is adjusted using 2 pins, SLP-SEN-A and SLP-SEN-B. SLP-SEN-A controls sensitivity of input pins TP0, TP7, while SLP-SEN-B controls sensitivity of input pins SP8, SP15. Capacitors need to be connected in the same way as discussed previously. The next settings are related to output type. These are not of much interest to us in this project because we are using serial interface and not the direct output mode. Output type may be active high or active low. The default is active high. This means the output pin becomes high when the respective input sensor is touched. One more configuration is output type, which may be set to CMOS, push-pull, open drain, or open collector. We don't need to bother much about this, as we are not using direct mode. Finally, few settings related to the sleep mode. Sleep mode is designed to save power and is important for battery-powered projects. Our project is not battery operated, so we will go for better performance settings rather than power saving settings. One setting is sampling at sleep mode, and we have an option of 8 Hz and 64 Hz. Since we do not need to save any power, we would prefer the 64 Hz mode. For that, we need to connect a resistor from WPSCT pin to ground. WPSCT pin is shared with touch input pin TP5. Another setting is sleep mode sampling length, which we can select as 4ms or 2ms. Here 4ms is default and okay for us, so we don't need to connect any resistor for this setting. That is all. I have discussed all the settings in detail, and now no more settings are left. Let us move on to the schematic design. Here you can see I have placed the IC in my schematic sheet. This IC is available in stock with JLC PCB assembly service, which is the preferred way nowadays to get your PCB fabricated and assembled with high precision. You can save time and have a pro-grade PCB for your prototype. So here I have also added a property to this component that has the JLC stock number in it. This saves my time, and when BOM, bill of material, is generated, we have this stock number of all components in its separate data column. Let us start by connecting its power supply and ground pins. Then we will add a decoupling capacitor between VCC and ground, and we will have us a 100 NF capacitor for this. These two lines, SDA and SCL, are used to transfer data to our main microcontroller. We connect them to GPI0 pins of microcontroller. Then we add capacitors like this to the SEN-ADJ1 and SEN-ADJ2 pins to adjust touch sensitivity to input lines TP0, TP7. since we are not using TP8, TP15, we don't need to add capacitors on other two pins, that is SEN, ADJ 3 and 4. After that, let us add capacitor in similar manner to SLP SENA pin to set the sleep mode sensitivity of input 0 to 7. Finally, we can connect the input pins to touch sensors. In this project, we are using touch sensor pins made on PCB. They are nothing but simple copper pads of about 10 mm diameter, thus easy to touch by fingers. As already discussed, we will also add a high-value resistor from TP5 to ground to select 64 Hz sample. Here it is. Done. Our hardware design is finished, so let us move to the software part. The software part is very easy, and we just need to write a piece of code to read the state of all 8 or 16 buttons from this IC to a variable in our code. As I have already told that this IC has two pins for data interference, the one is clock and the other is data. The microcontroller makes the clock like high and then read the level present on data line. In this way, MCU has one bit of data. After the microcontroller makes the clock line low, wait for some time and make high again and read the data again. In this way, it should read all the data bits, which is 8 for 8 button mode and 16 for 16 button mode. The data order is SLB first. That means the first bit read corresponds to button 0. Then next one is button 1 and so on. The range of clock frequency is 1 kHz to 512 kHz. To be safe, we will use a frequency of about 200 kHz. For that delay should be about 2.5 microseconds. That's all for now. Hope I have covered everything you need to know about this nice little chip that we would integrate into your project. Bye. See you again.